I would like to show you how you can use calculus to help you a little bit with the directions or the shape of graphs in the graphs of motion in your science section or the section of physics. I took two examples from your past papers, and let's look at them and let's look at the maths behind those questions. So the first question is when you have given a velocity time graph. There were obviously some questions based on it. At some point you had to draw the acceleration time graph. Maybe you also need to look at a displacement time graph from the given information. So we have a car that it's moving east, and as I analyze, as I look on the graph, I have 4 sections of the graph. So I've got a section 1, then the motion changes in a section 2, my motion changes again in a section 3. The velocity or the part of a graph between a section C and E has an x-cut at D, which means that the value of y is 0, so that's why my car is stationary. And I've got a section 4, which is then below the x-axis, since velocity have a direction. Alright, so what can we get mathematically out of this graph? Well, in the first part of a graph, the straight line AB, it's a straight line with positive gradient. So if I would like to write a mathematical equation, and forget about the time but write it in terms of x, I will say that I have a straight line y equals to positive gradient of x and some y-cut. Okay, in this case, the y-cut is 30, so we can be quite accurate. I don't want to be overly accurate. I'm just looking at what general information I can get. So if this is more or less an equation of a velocity with respect to time for the section AB, and you know that the velocity is a derivative of a distance, then the only time that you can get a positive 2x as you differentiate is if your displacement, if the function s of t was positive x squared, okay, because positive x squared will give me a derivative of 2x. If positive x squared, that means my displacement time graph must be a part of a parabola with arms up. Okay, hope you get it. Section 2, in the section BC, I have a velocity that is given to me as a straight line y equals to c, to some constant. In this case, that constant is 40. Now again, if the velocity is the derivative of distance, then in order to get a derivative equal to 40, my original function had to be 40x, okay? Which means that your distance was a straight line that was increasing, or the straight line with a positive gradient. Okay, section C, or from C to D, section 3. In this section, you are dealing with a straight line that has a negative gradient, okay, plus some constant. Now, if I need to get a negative gradient, that means that I started with negative x squared, because only then the derivative will give me minus x. Now, if minus x squared, then that means I was dealing with part of a parabola with arms down on the start of this motion, if I need to recreate the graph of displacement versus time. And then the last section, section number 4, so that's the DE. So I know that here my object was stationary, velocity was 0, it had the x-cut, and I continue with a negative gradient, which means that we will continue with the arms down if I want the displacement time graph. What if I want acceleration time? Okay, that's even easier, because remember that your acceleration using the calculus of motion, acceleration in respect to time is nothing else but the derivative of velocity. So if AB is a straight line, what will be the derivative of x or 2x? It will be just the constant. Okay, so in a section AB, I will have a constant positive acceleration because the gradient here is positive. In a section BC, I will have a zero acceleration because acceleration as the derivative of velocity, this is a straight line, so derivative will be zero. In a section CD, I've got a negative gradient, so I'm looking at constant negative acceleration, and so the same in a section DE. Okay, maybe a little bit confusing because you seldom think about maths in science, but if you pause it and you analyze this a bit, you can use a little bit of maths to help you to place those straight lines or horizontal lines for acceleration above or below the timeline as you will be sketching it in a physical sciences exam. Let's look at one more graph from the past papers. Okay, so this one was the velocity time graph that represents the motion of a girl riding her bicycle. She was riding in a northerly direction, so obviously north will be taken as positive. What can we say here about the acceleration? Right, again, remember that velocity, if I take a derivative of velocity, I will get my acceleration. So what happens in a section AB? In a section AB, the velocity is constant and it's equal to 5 meters per second. Right? We're doing maths. I'm not looking at units. So if velocity is 5, what will the derivative of velocity be? Well, the derivative of velocity will be 0, which means that my acceleration is 0 for this section. In the section BC, my second section, I have a positive gradient. So my velocity graph will be a positive x plus c. Boys, you obviously can find this equation, but you're not going to be looking for the equation on the exam. It's just that you know that it has a positive gradient, which means that as you differentiate the velocity to get acceleration, your acceleration in this example will be positive because the gradient here is positive. Derivative of m times x will then be positive. In the section CD, your velocity is again constant, so the velocity is equal to 10, which means that acceleration will be 0 because the derivative of 10 is 0. In a section D to E, in the section DE, we are looking at a straight line, so the velocity time will be a straight line with the negative gradient plus some constant. Again, so this is important for me. That gradient is negative, which means that if I was to differentiate to get my acceleration, I will get an acceleration that it's negative. So I will draw my graph below the time axis. Exact values, obviously you can find exact values because your exact value is nothing else but the gradient between 2 points that have given to you the coordinates, because it's all to scale. Think about it. At least going from the velocity to acceleration graph, it is really simple if you apply a little bit of calculus of motion. Moving from velocity back to displacement, little bit more complex, but it's still doable if you think maths and if you think calculus of motion.